Okay, so today our lesson is about work. All right, and so work goes hand in hand with energy, because as a matter of fact, when you guys gave me the definition on Tuesday about what energy is, y'all said it's what you need to do work. And then I said, true, but I also said we're going to kind of learn a little bit more about work later. Well, today's that later. So today's topic is work. All right, but just to kind of go ahead and make sure that we kind of say our piece in regards to what work is, take 5 seconds and think about how would you explain what work is to somebody. So if you're explaining it to a fifth grader, right? So, hey, what is work? What would you tell them? Okay, like from what you know, what is work? So I'll give you about 5 seconds. All right, so Nigel, what would you say work is? Without using the word again.
Doing something.
Doing something, okay. My devil?
When you put energy towards it, like effort.
Putting effort towards something, okay. All right, Coburn. You do work, so therefore, what is work?
Like a course.
Only y'all trying to think science. I'm saying explain it to a fifth grader, right? Like, what's work to you?
Things involving child. I don't know how to explain it.
You know how to explain it? Eric, go ahead.
The process in which you do something for a wanted outcome.
All right, the process in which you do something for a want or outcome?
Wanted outcome.
Or for a wanted outcome. All right, there you go. That sounds pretty lengthy and pretty, fancy. All right, anybody else? What is work? Anybody ever done work? How do you know you done work? You get paid? All right, what'd you say?
Because you got something out of what was done.
Because you got something out of what was done? Okay. Like, how would you know if you're doing work? Let me ask you now another question. And next question. Like, how do you know when you're doing work?
You out of breath.
When you're out of breath? Okay. Anybody else? Like, that's it? So you have a job, you do work, you out of breath?
No.
Then maybe you're not doing work. Maybe we shouldn't pay you. You know what I'm saying? Janie, when you get paid, so when they pay you because you're out of breath? No? All right. You know what I mean? Like, that's the whole issue, right? Like, work kind of means different things. So, some people may think doing construction is work, right? Some people may think, being a teacher is work, right? There's different things to what work is. But what we need to know is this. Work, all right, uses energy, all right, to create change. Okay? Work uses energy to create change. That's why work and energy go hand in hand, meaning what do you need to do work? Well, I need energy. Well, again, what is energy? Energy is what we need to do work. So they kind of go back and forth to one another. I need energy to do work. What do you need to do work? You need work. I need energy. So that's why energy goes along with it. That's another reason why work is going to be measured in joules. Okay? But what I need to do, though, is I need to get back to the first part of that definition where it says uses energy to create change. Okay? And so when we talk about the create change, all right, so I'm going to go right here. What I mean by create change is motion, okay, / movement. That's what we mean by creating that change. Work is when you apply energy, and that energy results in motion of something, okay? Something has got to move because of what you do. All right, and that's the important part. That's what makes work work. Because again, if I turn on the machine and the machine's stacking up all these boxes, well, I'm not doing any work. All right, even though if I didn't turn on the switch, the machines wouldn't work. Okay, but I'm doing work when my use of energy results in the motion or the movement of something. All right, now the energy where that comes into play is the use of force. Okay, the use of force. Because remember, we said, back when we learned test 2, remember we said we had the box with the 2 people on each side? And we said, what kind of, what has to happen in order for that box to move? Hold on, 2 people talking at the same time. Let me go to my angel.
Somebody pushing it or pulling.
Somebody's pushing. Well, on the box, on the diagram we had 2 people pushing on both sides, right? But what was the issue about the pushing on each side?
It was balanced.
It was balanced? That's what had to happen for it to move? It had to be unbalanced, right? Which meant somebody had to apply a force greater than the other one, right? But that's where force comes into play. So how do we get the motion? We get the motion through the force. But what do we need in order to get the force? We're going to need energy to get the force generated. Okay? And so that's where these 2 things are coming into play. Now, force, obviously, again, we measure in what unit? Newtons. So let's not forget that. All right? Motion or movement, we measure. Let me focus on the word movement instead. What do we measure movement in? Okay, he's going meters per second. All right, Coburn's shaking his head no. What do you think we measure it in? You doubt that's it? All right, he's not quite sure, but he doesn't think it's that. All right, huh? Joules. That's what we're measuring work in. All right, because work is a part of force, which is newtons, and a part of movement. Right? How do you know something's moved? This is like first day test 2 information. How do we know something's moved? Change in what?
Position.
Change in position, right? What do we call that change in position? Hold on. You're good. You guys are good so far. Now just kind of catch up with me. What do you call that change in position? Did your watch tell you? I mean, y'all making it seem like y'all think it's like something crazy. Change it. Look, ready? Here I am. Here I am. I just changed my position. What's that called, Eric? Displacement. Okay, what do we measure displacement in? That's what I'm saying, guys. Like I said, test 2 ain't over just because we added test 2. Stuff we learned in test 2 still comes into test 3. And it'll still come into test 4 too. What do we measure displacement in? Centimeters? Okay, cool, centimeters. Let's use centimeters, right? Even though we usually are using what part of centimeters? The meters, right? So again, meters. It's good, but centimeters is fine there, Alondra. So I'm not saying you're wrong. You know what I'm saying? You're right. It's just that the one that we usually use in our problems is meters. So force in newtons, movement in meters. We're going to see now that we're going to use these 2 together to calculate our work being done. Okay? However, though, here's the main thing I want to make sure we understand. Okay? So I'm putting a star here because now here's where we get to a real, like, if I'm going to give you a solid definition, all right, this is what I want it to be. Work is applying a force to an object to get it to move a distance. Okay? Work is applying a force. You have to apply it. That's why you need the energy. But you're going to apply that force onto something that you're trying to move. Okay? That's why, again, most of the time if you're moving somebody out of a house, you got to lift all them boxes, or you got to lift all those tables and those chairs and them sofas and those beds, right? Like, that requires force. That's why you require energy. That's why most of the time when you're moving somebody, you know, they're usually going to either they're going to bring breakfast for you to start off with energy supply, or they're going to buy dinner for you afterwards to replace the energy that you used. Okay, at least that's what they should do. Otherwise, you just free labor. All right. So applying a force to an object to get it to move a distance. Force, distance, newtons, meters. Okay. So we're going to see that come into play. All right. So that's why when we look, so here's what I want to do. I'm going to need some room for this part because I want to make sure we don't screw this up. So I'm erasing right here. We're still with work. You're just going to write underneath what we have right now. And here's the most important part, okay? Maybe I should cover up the microphone. I'm going to write a question. What needs to happen? Okay? Because here's where you get a trick question. So, as a matter of fact, I'll even write in your notes. Okay? Trick question. So that way, when I trick you, you can't say, oh, I didn't know, because I'm telling you it's a trick question. So if I'm telling you to expect it, you can't be surprised when it happens. What needs to happen? All right? The reason why this is a trick question is because of this. Just because something looks like it's doing work doesn't mean scientifically that it's doing work. Okay? Let me say that again. Just because something looks like it's doing work doesn't mean scientifically that it's doing work. For example, okay, let's say I had, only for the video purposes do I need to grab this. Let's say I had a stack of 10 of these chemistry books, okay? So I got a stack of 10, all right? All right, so, it's not a light thing, okay? So let's say I had Victor, okay, and I had him carry a stack of books, all right, 10 of these, all right, from my classroom over to Miss Hyatt's classroom, all right? Would you say he's done work? Okay. Donovan, would you say he might be breathing heavy at the end of that?
Yeah.
Yeah, okay. So again, most of us would say he's done work, right? Okay. Well, that's why I need you to know the answer to this question. Because he will have been doing work, but not as much as you think. As a matter of fact, the whole time he was carrying the books over to Miss Hyatt's classroom, he was doing work. Even though it made him tired. Even though he needed energy. Even though he was applying a force, he wasn't doing work. Because there are two things that need to happen. All right? Number one, okay? There are two things that got to happen. Number one, the object must move. That should be obvious. I mean, if the whole point of work is applying a force to move something, then the first thing that has to happen is that something better move. That's number one. Now, based on number one, when Victor carried them that stack of 10 books to Hyatt's room, those books were moving. They moved from my room to her room. Okay? So that would have fulfilled that obligation. But if you remember when we did significant figures, remember I had rule 4, I call it the and 1 rule, because it had to be at the end of a number and to the right of a decimal, right? It had to be both. It couldn't be one or the other. It had to be both, right? Well, that's the same thing here. What makes this a trick question is the two things that need to happen, they both have to happen. It can't be, well, one did and the other didn't. If they both don't happen, then scientifically, work has not been done, okay? And we're going to show you that to you when we do a little demonstration here. Today, depending on how much time we got, I'm not going to be sexist, okay? I'm going to have a demonstration, okay? And I'm going to have a man do the same work as a woman does, okay? Tomorrow, we're going to prove scientifically why man is stronger than woman, okay? And I always love getting those reactions from the ladies, okay? But tomorrow, we're going to prove scientifically why man is stronger than woman. Male is stronger than female. All right? Now, but again, right now the object's got to move. The second thing is this. This one might be wordy because this is where the technicality can come into play. All right? So you're going to have to follow me with this. I'm going to say here, the direction of the force must be the same as the direction of the movement. Okay? And that's the one where most things get caught. Like that's the one where Victor can be very tired at the end of that job, but at the end of that job, he has not done work. which is hard for us to understand because most of the time we think work and job are the same thing. But in this case, we're going to learn that the direction of the force must be the same as the direction of the movement. So for example, just for simple purposes of this video, okay, when I took this book right here that's on my desk, which you can barely see, but let's just say this, okay, so now I can see it on the video. See the book? Right? All right. That right there. See what I just did? What did I just do? I lifted the book from here to here, right? Which way did the book go? Up. Which way did I apply the force onto the book? Up. So the book went up. My force was up. Are they in the same direction? Yes. So therefore, for me to do this, that is work. So again, if I go right here and just go boom, that is work. Now, if I can see if I'm still in frame here, okay? If I do this, I'm holding the book, right? I'm holding the book, which means my force is going in what direction? Up. Now, I only heard one voice, which means some of you don't get that, okay? Here's why my force is going up. Because if I wasn't applying a force onto the book, which direction would the book be going? Down. Is the book going down? So something must be pushing it up. Who is it in this case? Me. I don't like gravity. Gravity is why I don't want to step on a scale. All right? So, I'm pushing upwards onto the book, correct? Now, when I go like this, right? Which way did the book go? Did the book move?
No.
Wasn't it over there? Isn't it over here? Did the book move? Yes. Which way did the book move? That way, right? What was the direction of my force? That way. Are they pointing in the same direction? So therefore, did I do any work? No. That's why when Victor were to carry 10 of these books to Miss Hyatt's room on the other side of the school, that's why he may be tired, but he hasn't done work. Because his direction, or let me rephrase that, the book's direction and his force direction are not pointing in the same way. All right? So do we understand that little issue right there? So that's why we want to remember that as well, okay? So these are the two things that need to happen. If the first one happens but not the second, work is not being done. Okay? If the first one happens but not the second, work is not being done. So let's take a look at the work formula. And then we will do a quick demonstration. I'll use different books because those I already have a weight for. All right, the work formula is W equals FD. Okay? Now, please make sure, if you have your reference sheet, that you find it on your reference sheet. Because again, on test days, all you get is the reference sheet. So if you don't know where it is, you may be looking there and, like, I had somebody on the last test for momentum, right? Don't write this down. Remember momentum is that lowercase p?
Yes.
Right. I had somebody use capital P, W divided by T, to solve for momentum. All right? Because they probably got confused. PP. Right? That's power. That's momentum. But they just used one that had a P because they didn't know where it was before, and then they used the wrong one. So that's why you want to definitely know where these things are on your reference sheet, because that's what you get on test day. That's what you get on game day. So if you suck at algebra, which a majority of us do, well, I shouldn't say us because I don't, but there's our triangle for those of you who need it. All right, and just as a reminder, because I'm hoping that at least one person watches this video, right? If I'm solving for work, what do I do with F and D? I multiply, okay? If I'm solving for force, what do I do with W and D? I divide. And if I'm solving for distance, what do I do with W and F? You divide, right? So again, that's how you use that triangle to help you out. W stands for what? Work. Work is measured in what? Joules. So we might want to remember that. Okay? F stands for what? Say what? Force. Okay, I don't know what some of y'all just said. Okay? Force. And, Allison, force is measured in what? You should be disappointed if Coburn gets this right. Coburn.
Joules.
Close. Eric. Hold on, what? Newtons. All right. And lowercase d stands for what? Distance. And Zyquez. Distance is measured in what? Meters. Yeah, it seems like I'm boring him now by asking him these questions. He's wanting that quiz. Everybody got it? That's how we do, that's what we're going to do. Okay? So, just as always, so I have one in my one video. All right, let me go ahead and get a work problem up on the board here somewhere. Victor, wait, I don't know. Can you reach that button? It's kind of further away. I have it further away on purpose this time now. You might have to bump that thing. George, you might have to straighten that thing out, you know what I'm saying? But just wait for it to show up first. This ain't the one I wanted. This is the one I wanted. All right, George, do me a favor. Just line up them edges. That's usually what I like right there. Thank you, sir. All right, so let's take a look. This one you do include in your notes so that you have it in your notes. Okay, so make sure you write this one down. Question says, how much work is done on a small car if 3,150 newtons is exerted to move it 75 meters to the side of the road? Well, obviously, just for the sake of, reminding ourselves about those two things that got to happen, if I'm pushing a car down the road, which way is the car going to be moving? Forward, right? And which way am I going to be pushing? Forward. Are they going in the same direction? Yes. Then work is being done. So if you're tired after pushing a car, congratulations, you did work. Okay? If you're tired after lifting a car, congratulations, you did work. If you're tired after carrying a car, I'm sorry, you did not do any work. Okay? However, if you can carry a car, then you are a freak of nature, as opposed to what some of you are, who are just freaks, based on your actions after school. Now, we go right here. We're solving for what again? Work. Jayla, give me the work formula again. W equals F times D. Okay, remember when they're side by side, they're multiplying. Some people keep thinking you're dividing. Okay, then we're going to list our variables. All right, we're going to list our variables, and we're going to get Nate to tell me what would I put next to D equals?
75 meters.
75 meters. All right, there we go. Figured I'd change it up. Most of y'all used to me starting from the top to the bottom, so I figured I'd start from the bottom to the top. Let's go to Deshanti. What am I going to put next to W equals? X. All right. Good job. All right. And then let's go to DeRosier. What am I going to put next to F equals?
3150 newtons.
3150 newtons. Okay. So this is my setup. If I go over here and rewrite this formula but use my numbers instead, I'm going to get X equals F, which is 3,150, times D, which is 75. All right. Victor, I know you got a calculator. Go ahead and multiply those two numbers for me and tell me what number do you get. And this is Victor, so don't let anybody else steal his moment. Just read me the numbers.
23625.
That?
Yeah.
That right there exactly?
Yeah.
Okay. You sure we're not missing a zero?
Yeah, there should be zero.
I think there's a zero in there. Double ready? Here's what I'll do. I had this rule in chemistry class. It's called the Sandra Rivera rule. Double check it. Type it in again and see if you get the same answer twice.
Oh, I did it.
Okay, see what I'm saying? That's why we want to make sure. So we got that right there. 236,250. What there, my devil?
Huh?
What? 236,250
Joules.
joules. There you go. All right. Joules. Yet somebody might say, but hold on, we ain't solving for kinetic energy or potential energy. But again, what do you need to do work?
Force essentially.
Sorry. For the one time I wanted you to say the word, you need energy to do work, right? That's why work is measured in energy. Because that's what you're measuring. You're measuring how much energy did you expend to apply that force to move that object. Got it? Oh, good. Alrighty then. That concludes the recording of this video.